Question 1. A crowd gathers around a movie star, forming a circle. The radius of the crowd increases at a rate of 9 meters per second. How fast is the area taken up by the crowd increasing when the radius is 5 meters? So, let's underline what we know. We know that our problem involves a circle. We know that the radius of the crowd is increasing at a rate of 9 meters per second. And we want to know how fast the area is taken up by the crowd increasing when the radius is 5 meters. Now that we have it underlined, let's write down the information that we know. We know that it's a circle. We know that the radius is increasing at a rate of 9 meters per second, which we then write as dr over dt equals 9 meters per second, with dr dt meaning the change in radius in respect to time. Next, we're going to write down the objective of the problem, which can be found in the last sentence, which is how fast is the area taken up by the crowd increasing. That can be rephrased to what is the rate of the area increasing, which can then be written as dA over dt equals question mark because we haven't figured it out yet. dA over dt represents the change in area in respect to time. Then we can write that we know that the radius of the crowd / the circle is 5 meters. And finally, we write down the area of the circle, which is A equals pi r squared. You're either given this formula or you can just look it up. Let's draw a representation of the problem. Let's draw the movie star right here, and then the crowd around the movie star. So this right here is the movie star. So this right here is 5 meters. That's the radius. So with this information, we're trying to find out how fast the crowd is increasing. Now we're going to get into the problem. Let's take the formula for the area of the circle. So A equals pi r squared. Let's write d over dt times A equals d over dt times pi r squared. We're doing this to derive. So once we do this, we use the power rule. So this becomes dA over dt equals 2 times pi r to the power of 2 minus 1 times dr over dt. I wrote the process of the power rule out just so people can see what I did. It's not necessary, but I did it anyway. If you are unfamiliar with how the power rule works, to refresh your memory, the power rule looks like this. After we rewrite what we've done, it becomes dA over dt equals 2 pi r to the power of 1, which, to the power of 1 is a bit redundant. I'm just doing that so I can see. Times dr over dt. Next, we plug in the values from here. So we don't know what dA over dt is, obviously, because that's our objective. See here, dA over dt equals question mark, so we don't know what it is. We leave that. We write 2 pi. We do know what r is, our radius. We know that it's 5 meters, so we plug in 5. And then we do know what dr over dt is from here, which is 9 meters per second, so we plug in 9. So from here, we multiply everything, except leave the pi as constant. We get dA over dt equals 90 pi meters squared per second. And that is your answer. Question 2. A spherical balloon is deflated at a rate of 256 pi over 3 centimeters cubed per second. At what rate is the radius of the balloon changing when the radius is 9 centimeters? Let's underline the information that we think is important and then transfer that into bullet points. We know that the volume is decreasing at a rate of negative 256 pi over 3 centimeters cubed per second. This is negative because the spherical balloon is deflating. This can be rephrased as the change in volume in respect to time. We know that our objective is to find the rate of the radius increasing, which is the same thing as we have to find the change in radius in respect to time. We also know that our radius is 9 centimeters. Finally, we have to write down the formula for the volume of the sphere, which you can Google. It is V equals 4 over 3 pi radius cubed. Let's do a quick drawing to represent the problem. This is a spherical balloon, so draw it in the shape of a sphere. The radius is 9 centimeters. and it is deflating. So here's the imaginary deflating image. It isn't necessarily super important, but it kind of gets the point across as to what is happening. Again, we are looking for the change in radius in respect to time. To begin the problem, let's rewrite the volume of the sphere, and then d over dt, the equation. After you use the power rule and multiply the things together, you get dv over dt equals 4 over 3 times 3, which is the same thing as 3 over 1, pi r to the power of 3 minus 1 times dr over dt. So if you solve that out, you get dv over dt equals 12 over 3 pi r squared times dr over dt, which you simplify to dv over dt equals 4 pi r squared times dr over dt. Then you plug in the known values. We know what dv over dt is, negative 256 pi over 3, then 4 times pi times 9 to the power of 2 in parentheses times dr over dt. What the two sides of the equation have in common here is the constant pi, so we get rid of those. There is 4 in both sides of the equation, so we reduce that. Negative 256 over 3 becomes negative 64 over 3, and then we are left with the 81 and dr over dt. From here, we can divide 81 on both sides. To divide a fraction, you just use the reciprocal. 1 over 81 times negative 64 over 3 comes out to be negative 64 over 243. We are left on the other side with 1 times dr over dt. So if we move dr over dt to the left side of the equation, we find that the change in radius in respect to time is negative 64 over 243 centimeters per second. Question 3. A 25-meter ladder is leaning against a wall and sliding towards the floor. The top of the ladder is sliding down the wall at a rate of 7 meters per second. How fast is the base of the ladder sliding away from the wall when the base of the ladder is 7 meters from the wall? Let's underline the important information. After that, let's draw a representation of the problem, because I think that's necessary before writing down the stuff we know into organized bullet points. So I drew a wall and a floor, so the ladder is leaning against it. I assigned 3 letters to represent the 3 sides in this problem. It forms a triangle. Now let's go back to writing the bullet points of the stuff we know. We are told that the ladder is 25 meters, and I chose z to represent the ladder, so z equals 25 meters. We're also told that the top of the ladder is sliding down at a rate of 7 meters per second. So that means if you look at the drawing, the top of the ladder is sliding down. That would involve our y. So the change in y in respect to time would be negative 7 meters per second, and is negative because the y is decreasing. Our objective is to find the rate of the base of the ladder sliding away from the wall. Because the base of the ladder is by the floor, x would be involved. So the change in x in respect to time is unknown. Last but not least, we are told that the base of the ladder is 7 meters from the wall. If you look at the drawing, we can see that base of the ladder from the wall, x would equal 7 meters. Now that we know the lengths of the 2 sides of our triangle, we are able to use the Pythagorean theorem. So x squared plus y squared equals z squared. You might have heard it as a squared plus b squared equals c squared. You just substitute the letters for different letters. You get 7 squared plus y squared equals 25 squared. Comes out to be 49 plus y squared equals 625. You subtract 49 from both sides. You get y squared equals 576, square root that, and you get y equals 24. So now we have all 3 sides' lengths. Now that we have this, we use the formula below to get our answer. Using the formula, we plug in our known values. We plug in 7 for x. We still don't know what dx over dt is. We plug in 24 for y because that's what we just solved for using the Pythagorean theorem. Then we plug in -7 for dy over dt, and for z we plug in 25. For dz over dt we plug in 0 because the latter is not changing in length. Then we multiply what we can, get 14 times dx over dt minus 336 equals 0. Add 336 to both sides of the equation to get it ready for solving. Then divide the equation by 14 on both sides. And in the end you get dx over dt equals 24 meters per second, which essentially says when the base of the ladder is 7 meters from the wall, the rate of the base changing is 24 meters per second.